All right, so we were talking about these incidence Hopf algebras that you can build from graphs. So we were saying that if you start with a family of graphs, that's called a hereditary family. And so in this context, hereditary means that it's closed under deletion of edges, contraction of edges, and disjoint union. Okay. If you have this, then and maybe, I mean, it's possible that you can do this in a greater generality, but I'm going to mod out by this. I'm going to mod out by isomorphism, ignoring isolated vertices. Okay. So two graphs are going to be considered equivalent if, when you delete all the isolated vertices, then they end up being isomorphic. Okay. Then we consider the span of the family, and we can make this into a Hopf algebra where the product is given by the disjoint union and actually, even though the basis elements are graphs modulo isomorphism, that's why I put a little bracket around them. Let me just forget about those brackets, okay? So just remember that the basis elements here are just isomorphism classes, and then I multiply them like this. Okay, so multiplication is disjoint union, coproduct, the coproduct of a graph is the sum over the flats of the graph of the restriction to the flat tensor, the contraction of the flat. And the unit, the empty graph, and the co-unit is 1 if the graph is empty, and 0 otherwise. Okay. And so this is a Hopf algebra. And what I want to do today is consider a special case of this. And I'm going to call it example 8, because this is the next in our series of examples of incidence Hopf algebras. And this one is called the Faa di Bruno Hopf algebra. And this is the only theorem that I know named after a saint. So Faa di Bruno was a priest, and at least I think it's true. Maybe we should check that, but I think it's true that he was canonized recently and is now a saint. And he didn't quite invent the Hopf algebra, but he, I mean, I'll tell you why it's named after him. It was actually Giancarlo Rota who gave this Hopf algebra that name. But what I'm going to do is consider this construction for a particular family of graphs. And the family is going to be the disjoint union of complete graphs. Okay. So what is this the complete graph? Kn has n vertices and all edges between them. All n choose 2 edges between them. Okay, so for example, K5 is the pentagon with all the diagonals. Okay? And what I'm going to do is that I'm going to consider all the ways of taking unions of these things. Okay? So I claim that this is a hereditary family of graphs. It isn't actually. Can you see where this is not a hereditary family of graphs? Is it closed under products? Well, it needs to be closed under. I mean, what is products? Remember, product here is disjoint union. So is this closed under disjoint union? It actually is, because if you take a union of complete graphs and another union of complete graphs and you take their union, then that's a union of complete graphs. Remember, hereditary here means it's not taking products of graphs, it's taking union of graphs. Yeah? I mean, the elements here are not individual complete graphs, they're just, a bunch of complete graphs. Okay? So it is closed under disjoint union. It is closed under contraction because if I take an edge here and I contract it, then I get 4 vertices and all edges between them. So the contraction of K5 is K4. Is it closed under deletion? No, because if I delete a single edge, then that's not a complete graph anymore. Okay? So let me say this a little bit differently, because I don't actually need. What do I really need for this to work out? I just need that if G is a graph and F is a flat, then G restricted to F and G contracted F are in my family. Okay? And so really what I need is that restriction to flats, contraction of flats, and this joint union. If I'm closed under these things, then this operation makes sense. Okay, and I claim that this is closed under restriction to flats. Okay, because what is a flat of Kn? Let me draw a flat in blue. Okay, so for example, is this a flat? Remember, what a flat means is a set of edges such that if you contain all but one edges of a cycle, then you also contain that last edge. Okay, so this is not a flat because if I contain this, if a flat contains this and this, it has to contain the whole cycle. It has to contain this guy also.
There's another way of thinking of flat as a closure of something, closures in some.
There is another way of thinking of flats as closures, and I will say more about that, but maybe for now it's not too important, so I don't want to go into that at this point. We'll talk about it later. So that's a flat, a little triangle. Is this a flat? No, right? Because if a flat contains this and this, it also has to contain this. So is this a flat now? Yes? Are you sure? Here I have a cycle, right? And if I contain this blue edge and this blue edge, then I also have to contain this blue edge. It's a complete subgraph. That's a nice, simple lemma, is that the flats of Kn are just the complete subgraphs. Okay? And so that means that if I restrict to a flat, then I'm going to get, actually, what is, no, a flat is a disjoint union of complete subgraphs, actually. Right? Because, for example, another flat is this guy and this guy, right? Because I contain no almost complete cycles. Or for example, this guy and these four edges also form a flat, right? Because there's no cycles that you can close. And so the flats of Kn are precisely the ways of putting disjoint complete subgraphs in there. Okay? That's a nice, easy lemma. And that means that this is closed under restriction to flats, because a flat is just a bunch of complete subgraphs. Contraction of flats, we said that that's also a disjoint union of flats and disjoint union. Okay? So when we apply this construction to this hereditary family of graphs, we're going to get a Hopf algebra. And that Hopf algebra is called the Faa di Bruno Hopf algebra. Okay? So Faa di Bruno Hopf algebra, I'm going to call it F, and it is what I get when I apply this. Okay? Question? I'm sorry? I don't, because what I need. So the question is whether I mean to write this disjoint union of flats here. I need to put these three conditions so that these operations are well defined. So product is well defined if given G and H in my family, the union is also in the family. So that's why I put this disjoint union. And the coproduct of G is well defined inside my family if whenever I take a G in my family, then this is in my world. In other words, the restriction to a flat and the contraction of a flat are in this universe of graphs that we're considering. Okay, so this is the Faa di Bruno Hopf algebra. Can you tell me what are generators for this guy? Generators as an algebra. We need a first of all, are all complete graphs enough? So if I consider the family of complete graphs, is that a generating set for this?
May I ask quite an interesting question? So given any complete graph, is it always isomorphic to K something? K some n?
Yeah, so the definition of complete graph is that you're isomorphic to this, to a Kn. So these guys generate the algebra, right? Because any disjoint union of complete graphs is just a union of these guys. And union in here is product. Right? So for example, this is a basis element of the Faa di Bruno Hopf algebra, right? It's a disjoint union of complete graphs. How do I generate it in terms of these guys? Well, it's just K5 times triangle times edge. Right? So given these guys, by multiplication, you get all of these guys, and then by linearity, you get all of K. So these guys are definitely generators. And I also claim that these are all necessary. In other words, I mean, and that's pretty clear. You cannot generate a Kn as a product of other things, because product here is disjoint union, and you cannot express a Kn as a disjoint union of smaller subgraphs. Okay? So these are the generators as an algebra. Okay? And I could keep drawing them, but it's going to be a little bit easier if I give them names. Okay? So the names that I'm going to give them are x sub 0, x sub 1, x sub 2, x sub 3, etc. Okay? So you might find it a little bit strange. I certainly found it a little bit strange why I call the complete graph K4 x3 instead of calling it x4. Can you think of why I want to call it x3 and not x4? The reason is that this is a graded Hopf algebra, right? What is the degree 0 thing here? X0. What is a point? Remember that in isomorphism we're ignoring points. So the point is the same thing as the empty graph. Okay? And so this is the number 1 in the algebra. So it has degree 0. And because it has degree 0, I want to call it x0. And this guy I want to call it x1, and the grading really looks like this. Okay? So that's why I call them like this. Now, so what is the product? Well, you can multiply these guys in any possible way, and there's no relations between them. Okay? So the product is the free commutative product on x0, x1, x2, etc. Okay, so the elements are just products of x's. Now, what is the coproduct? I need to figure out what is delta of something. And again, because I have generators as an algebra, it's enough for me to figure out what delta of xn is. Because if I know what delta of each one of the generators is, then using the delta's multiplicative, I'll have delta of anything. So delta of xn is given by this equation, right? So xn is the complete graph kn plus 1, and I need to sum over all the possible flats. So I'm gonna write the equation here. I'm gonna write the result here. But let's think about this for a minute. I need to sum over the flats of kn plus 1. And then I get kn plus 1 restricted to f tensor kn plus 1 contracted f. Yep. Because of this, right? So xn represents the graph of kn plus 1 vertices. This whole class, there's going to be an annoyance of going from n to n plus 1, and hopefully you can help me keep it straight. Okay, so what is easier, restriction or contraction? Well, if we go back to here, we talked about how if you contract an edge of K5, you just get K4. If I contract another edge, I get K3. If I contract another edge, I get K2. Whereas if I restrict, I get these disjoint unions. So it actually seems like contraction is easier than deletion, which is a little bit strange. Contraction is a little bit of a more subtle operation, but in this realm, it's a little bit easier. Okay? Let me here's K6. Okay? Let's take a flat. So a flat is a disjoint union of complete subgraphs. So maybe I can consider this flat. Okay? So F is my blue flat, and here I have K6. Okay? So what is K6 restriction F? I just restrict to the blue edges, right? So I just get a triangle, an edge, and a point. Okay? And remember that the point doesn't really matter if it's there or not. The point is that it doesn't really matter whether I put it or not, because you'll see why I want to put it, but this graph is equal to this in this algebra. Okay? We ignore points. What is K6 contract F? What is it? What happens when I contract all the blue edges? What do I get? I get we talked about how every time you contract an edge, you get a complete graph. And so we just have to say K how many? How many vertices do I get? It's K3, right? Because these guys get merged into 1, these guys merge into 1, and this gets merged into 1. So this is just K3. Okay? So in general, K6 mod F is what? K how many? What is this 3? The 3 is just how many disjoint pieces you have here, right? So this right here is K sub number of pieces of F. And this is just F, whatever F is. Okay? But that's where I say that this is a little bit easier than this. This is just a K something, and this is just a bunch of terms. Okay? Now, imagine that I do this over all possible flats of K6. Actually, let's just do it. So how can I get an X3 here? Sorry, in this case, I get K3, which is X2. What are the different ways of getting an X2 here? In other words, getting a K3 here? All the ways to partition 6 into 3. That's right. All the ways to partition the 6 vertices into 3 groups. Now, what are the ways of doing that? Well, if you partition a set of 6 into 3 sets, what are the possible sizes of the sets? One possibility is this one, 3 plus 2 plus 1. Okay? If you use 3 plus 2 plus 1, then you're doing exactly this. Your flat looks like this, and what does this look like? Kn plus 1 restricted to F. It looks like this is X2, this is X1, and this is X0. So I get X2, X1, X0. I mean, when I do this tensor this, I get X2, X1, X0, tensor X2. Question, Krista?
Yeah, Federico, the product of F and 6, what's the
5, thank you. Keep checking with me. Keep making sure that I do this correctly. This is the graph K6. So first of all, this graph contributes X2, X1, X0, tensor X2. Do we agree? This is x2, x1, x0 is the restriction, and the contraction is x2. Now, how many times do I get this term? Because this is only one particular way of splitting into 3 and 2 and 1. How many ways are there to do that? 12. It's a nice combinatorics question. So first I have to choose who's the triangle. So that's 6, choose 3. Then I have to choose who is the point. So I have 3 options, and then the other edge.
Can you choose every group of 3 for the triangle?
Yeah. It's a complete graph, so any group of 3 is the same. And so I choose any triangle, 6, choose 3. I choose who the point is, and then this gets determined automatically. So this is 6 times 5 times 4 over 3 times 2 times 3, 60. Okay. So there are 60 flats that look like 3 plus 2 plus 1, and that means that I have 60 contributions that look like this. 60 x2, x1, x0 plus. Let's look at a different kind of flat. So how else can I split 6 into 3 numbers? 4 plus 1 plus 1. Okay? So if I consider a 4 plus 1 plus 1, that would look like this. What's the contribution to the left-hand side? What is the restriction? Well, the blue graph is called x3 times x0 times x0. Okay? And by the way, x0 is 1. We just talked about how x0 is 1, so let's actually just drop it. Okay? So all I get is x3. Okay? And that's the contribution of a flat that looks like this. How many flats do I have that look like this? 6, choose 4. And it's just 6, choose 4, actually, because as soon as you choose this, then these 2 are determined. How much is 6, choose 4? It's equal to 6, choose 2, which is equal to 15. So you have 15 flats that look like this. Okay? Are there other ways of saying 6 equals something plus something plus something? I can't do 5. I can't use 5 because I can't use zeros, right? So the only other way is 2 plus 2 plus 2. Okay? So what does a flat 2 plus 2 plus 2 look like? It's just 3 edges.
Why can't you do 5 plus 1?
We need 3 parts, because I'm looking at ways of doing it with 3 parts.
Okay.
Yeah? So with 3 parts, if 0 cannot be a sum and this is the last one, 2 plus 2 plus 2. So what does that contribute? Well, these are 3 individual edges. So that gives me an x1 cubed. And what's the number of ways of choosing 3 edges in K6? Well, first I choose 1. Yeah?
Is it complicated by you can't put them anywhere you want now, because if they touch, then they have to close?
That's right. I have to choose 3 edges, but they have to be disjoint from each other. So I choose the first one, 6, choose 2. I choose the next one. So yeah.
I just don't see why 6 choose 2 for first one.
So I choose 1 edge. So out of the 6 elements, I choose 2 of them. And so that gives me one of the edges. Okay. Out of the 6 vertices, I choose which 2 to join.
Yes,
Yeah.
so you can't complete this one.
Now, for the next one, how many options do I have? Well, I have 4 remaining vertices, and out of the 4 remaining vertices, I should choose 2 of them. And then the other one is 2 choose 2, which is nothing. Okay? So I mean, you could write it, but I don't have to. So this is 6 plus 5 over 2 times 4 times 3 over 2. Okay? Is this the right answer, though? Well, the thing is that if I choose 3 edges, they don't know what order they were chosen in. Right? I chose first this one, then this one, then this one. But I'm overcounting by a lot, because that's the same thing as choosing this one, then this one, then this one. Right? How many times did I overcount? 6 because there are 6 possible orders to choose those 3 things. So I should divide by 3 factorial, which is 6. And so really, what I get here is 15. Okay. 15. And so these are all the possible ways of splitting into 3 groups. So these are the things that contribute an x2. Okay. I'm not done because I need to do this in every possible way. So then what I should do next is figure out how can I write 6 as a sum of 2 things. And when I do that, I'm going to get the part that is tensor x1. And actually, I think I might have done this. No, maybe I didn't do it. But I think it's a nice exercise for you to practice with these things. So you get something tensor x1, something tensor x0, something tensor x3 maybe, and so on. Okay. Okay. So yeah. Right, so that's a great question. I mean, this seems like a very natural question that probably somebody has thought about before. I hope you're seeing that there's some nice combinatorial questions that come out, and so the answer is a very combinatorial thing, and there is a name for this. These are what are called partial Bell polynomials. Okay, so in general, what you're going to get is things that look like this. So you get sum from k equals 1 to n of something complicated, tensor xk. So what is the complicated thing? It's not that complicated, but it's certainly more complicated than xk. You get this thing. I mean, it's just a polynomial in the xi's, right? It's a polynomial. So do I want to start that at 0? X1, I think I do want to start at 0, yeah. Because I can contract all the way down to having a single point. Where these things are the things that are appearing here. Okay, this, for example, this guy right here is B63 of 1, x1, x2, etc. Okay, so what are these things? What are these partial Bell polynomials? Partial Bell polynomials are B and K of y1, y2, y3, etc. is equal to the sum of some coefficient times y1 to the j1, y2 to the j2, etc., summing over all the possible values of j1, j2, etc. So far I haven't said anything. I'm saying this is a polynomial, and the terms look like this, and this is the coefficient of this term. Okay? But the important thing is what these coefficients are. So B, J1, J2, etc. is the number of ways of splitting an n set into k groups, k subsets. J1 subsets of size 1, J2 subsets of size 2, etc. Okay. So exactly what we just did. So let me then write. And so in particular, a consequence is that J1 plus J2 plus etc. should be equal to K. And also that 1 times J1 plus 2 times J2, etc. should be equal to N. Okay? So maybe I'll ask you to just record this into your mind. I'm going to rewrite it later. But this is an example of what these polynomials look like. But what I should say is that there is a formula for this number, which we kind of already did. Because what we're doing is we're saying, okay, you have your n elements, and you have to split them into a bunch of sets. So there's a bunch of sets of size 1. There's J1 sets of size 1. There are J2 sets of size 2, etc. So that's just a huge multinomial coefficient saying split n into the sets of the prescribed size. Is that the answer? Well, it isn't quite the answer because of what we saw, that sometimes you are overcounting here. Because these sets don't care what order they're in. And here I'm putting them in an order. They don't care what order they're in, so I need to divide by all the possible orders of these guys. These guys don't care what order they're in, so I divide by the order of these guys, etc. So this is, these are the partial Bell polynomials. And the coefficients are very explicit. They're given by this. Yep?
Why is it called partial Bell polynomial?
It's a great question. So there should be some non-partial ones. So the ones that are not partial, what is called the Bell polynomial is just, well, maybe I'll write it here. The Bell polynomial is Bn. It's just the sum of all the possible Bn k's over K. Okay. So these are partial Bell polynomials, and
Does that mean that we sort of end up with a full Bell polynomial just split up by two different ways of parts of the
that's right. So if you take this expression over here and you just forget this right-hand side, then you basically get the full Bell polynomial. Right? You're just summing over K all the possible partial Bell polynomials, and then they just get grouped according to what the value of K is. That's right. Okay. And so the point is that, again, we have this general framework for constructing Hopf algebras. We look at maybe the simplest example of a family that is, what are the simplest graphs? Well, maybe the simplest is the ones that have no edges, and then maybe the next simplest ones are, I don't know. These are certainly among some of the simplest things. And then if you want to understand the Hopf algebra structure, you're precisely led to these partial Bell polynomials. Somehow partial Bell polynomials are equivalent to understanding the coproduct here. Right? That's exactly what we're doing. Okay. So now what I would like to do is show you some very nice properties of these partial Bell polynomials, because they certainly predated this Hopf algebra considerations here. In fact, I told you Faa di Bruno was a saint, and it takes a while for you to become a saint, which means that this is old, right? His work is old. He's from the 1850s, and he already ran into these partial Bell polynomials in a context that seems very different, but I'm going to show you is not different. Okay, so let's see. Some nice facts, fun facts about partial Bell polynomials. Let's see. Maybe let's start with the Faa di Bruno formula. In its first version. And this goes back to very elementary calculus. Let me show you something that is not the Faa di Bruno formula. So I'm going to write something that is not this, and I'm going to erase it. So you certainly know the product rule for taking the derivative of f times g, right? F prime g plus g prime f. Do you know the formula for the nth derivative of fg? This is not the Faa di Bruno formula, okay? Let me make a comment that I sometimes just write sum over k. Is this good? I think it's good because basically this term only makes sense if k is an integer between 0 and n. So it's kind of implicit that k goes between 0 and n. So this is how you take the iterated derivative of a product. Okay. Now, does anybody know how do you take the iterated derivative of the next thing that your calculus students love? Composition. So if it was the first derivative, that's called the chain rule. So what about the nth chain rule? Well, this is what Faa di Bruno figured out. And it looks like this. So sum over k of, for example, what does it look like for n equals 1? It just looks like this, right? F prime of g of x times g prime of x. This is if n is equal to 1. But now if n is bigger, then you're going to do the sum over k from 0 to n. And now this term looks the same, but it's the kth derivative. And this term gets more complicated. But it gets complicated in a way that we should be very excited about, because you get exactly the Bell polynomials, the partial Bell polynomials. Evaluated at the derivatives of g. It's pretty cool, no? Again, I think this points to the fact that these polynomials are extremely natural, because it's a very natural question to ask what is the nth derivative of a composition, and if you want to know the answer, you just have to learn. You have to discover partial Bell polynomials, right? So that's the version 1 of Faa di Bruno formula. Okay. And this, there's several different proofs, and for example, one proof you can do is just do it by induction, right? Just to prove the next one, take the derivative of this, and then you see what needs to be equal, and that's gonna show to you that you should prove a recurrence for the b's. And so, if you try to prove it by induction, you'll discover a recurrence for the b's that you need to prove, and you won't have too much trouble proving it because we know what the b's are. Okay? So it's a nice exercise in kind of combinatorics and what people call manipulatorics, manipulating generating functions and keeping track of the combinatorics in between. So that's the first version of the Faa di Bruno formula, a second version looks like this. If f of x is given by this power series, and g of x is given by this power series, then what's the power series of the composition? It's what you get when you take this and plug into here, right? That's what it is. But it turns out that, again, the partial Bell polynomials do all the bookkeeping for you, and all you get is the sum. So is there a reason that we're excluding the constant term here? The answer is yes, because if you have a constant term here and you plug it into here, then at least as formal power series, that's not going to make sense, because you get an infinite sum of constants. Okay? So that's why you shouldn't have a constant term here. And here it doesn't really matter. If you have a constant a0, then that's just going to be a0 here also. So there is a reason to exclude it here, and there's not a reason to exclude it here. So what you get is this. So again, the power series of composition is given very precisely by the partial Bell polynomials. Okay. Now let me give you a third formula, which maybe I won't try to squeeze into here. You guys can remember this stuff, yeah? Or maybe I'll leave this formula here and erase everything else. Yeah, so that's a good point. If I plug into here, I mean, I write it as dot, 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 and I might mean that this is a formula in infinitely many variables, but I don't mean that. And we computed B63, and we found that it's not infinite. It really stops. Okay, why does it stop? Because how many terms could you possibly have here? At the very most n, right? You're splitting the set of size n into at most n things. Okay? And so at most we're using n variables here. And in fact, you can see that in n and k, you're using exactly n minus k variables. And so I could have stopped at yn minus k, and I just think the formula looks a little bit uglier there. So I didn't bother. But this is a finite set of variables, yeah?
If you extend past that limit, would b just go to 0?
B doesn't go to 0. It's just that the other variables never appear. Yn plus 1, yn plus 2, they never appear.
So you said you could have stopped it at n minus k, but when you're doing some of the other terms, it seems like you could still end up with like y sub n minus 1, regardless of what k is.
No, you should think about it for a minute, and you'll see that really the largest one that appears here is yn minus k. For example, we computed B63, and the largest thing that appeared was y 4. It might be n minus k plus 1. Yeah?
This is making the implicit assumption that for I less than or equal to n minus k, I is greater than or equal to 1. Right? Like that you don't have 0 terms at the beginning.
That's right. It basically comes down to the fact that you don't have 0 terms. And so that's what limits you to not have a lot of parts. Okay.
Why do you want to look at these kinds of generating functions?
Why do I want to look at this? Isn't it beautiful?
Just power series, but why of that form?
Because it's beautiful. No, because it's beautiful and it's very natural, I think. I mean, if oh, I see. Okay, so two questions here. One, when I saw these formulas, I really felt ripped off that I wasn't taught this in my analysis class or in some class. And I think basically the problem with a formula like this is that it doesn't fit squarely into an analysis class, because then you would have to teach people combinatorics, and it doesn't fit into a combinatorics class because you would have to teach people analysis. And so it just kind of falls between the cracks. And I think this is a very fundamental formula that never gets taught because it's kind of somewhere in between things. But I do think that there is, and I should say that in combinatorics, actually, there's a whole branch of combinatorics called analytic combinatorics, and this is extremely natural to do there. Your other question is, why am I dividing by n factorial here? And one reason is that I can, right? Any power series, instead of calling the coefficients an, I can call it an over n factorial, and you can't stop me from doing that. But it happens that for a lot of combinatorial generating functions, what is natural is to do this, and the an's are integers. Okay? And so in many combinatorial settings, in a way which I could make more precise in a different class maybe. Actually, let me rephrase. I think a very interesting project would be to understand explicitly why in many combinatorial applications the kind of power series that we like to use are what are called exponential generating functions of the form x to the n over n factorial, instead of the classic generating functions. And there's combinatorial reasons for this, and I can point you to there's a paper of Doubilet-Rota-Stanley that explains this very nicely. And sometimes the kinds of power series that you want to use are different. Like sometimes you want to do x to the n over n factorial squared, or there's different kinds of generating functions that are natural for different combinatorial problems. And that has to do with the Hopf algebra, actually, in a way that you can explore in a project, I think. Yeah. The other great place to, if you look at Stanley's Enumerative Combinatorics, Volume 2, it starts with this, and it explains why that's very natural. Okay, I want to show you another formula. That again, it's debatable whether this formula is an analysis or in combinatorics. It's somewhere in between. And it says the following. It says, let's say that let f of x be a sum like this, and okay, so this is some power series, and for some reason I would like to put the fn minus 1. I told you that there's a slight shift from n minus 1 to n here, but this is just any power series. I see what your means. A formal power series in T, right? And let's say that you want to know the power series for the inverse function. Okay. And it's easy to see that as long as f0 is not 0, then this really has a unique inverse function. So there's a unique function that you can put into here to get t back as formal power series. And I'm going to tell you what the coefficients are. The coefficients are, so each coefficient of here is this. And I should tell you that there's many formulas that people call Lagrange inversion formula, and this is one of them. F0 and G0 never appear. In here? Oh, another thing about this is that if your linear term is a, or I mean it is f0, then that just translates it translates multiplicatively into a term here. So one thing you can do easily is assume that f0 and g0 are 1, and I think that's what I'm doing. But probably what I should do is put f0 here. I think this is. Well, no. No, I'm sorry. Let me assume that f0 is 1. Okay. Now I remember what it is now. So I'm going to assume that f0 is 1, which, as I said, it doesn't harm me. If f of t is a scalar multiple of this, then actually you learn in pre-calculus how to take the inverse function of a scalar times a function. So you just do that here. So you can assume f0 is equal to 1. And if so, then this is the formula. Okay? Let me make the point that this thing that I just wrote down is how I started my class last time. Yeah? I wrote so when I started class last time, I said, okay, let's say that you have the formula y equals x plus ax squared plus bx cubed, etc. And then I invert it, and I get x equals y plus ay squared plus by cubed, etc. And then I give you some recipes for how to compute these things, and if you look at it, the recipe I'm giving you is exactly this one. These guys are the f's, and this is the inverse function. And so these guys are the g's. And so when I told you, for example, that I gave you formulas. A is equal to something, B is equal to something. C is equal to 5ab minus C minus 5a cubed, etc. The formulas that I'm writing down are exactly these formulas. I'm just cleaning them up a little bit, but this is, the way you compute these is exactly by just working out what these Bell polynomials are and plugging in. Question?
Yeah, so last class you started off with this question about finding these coefficients.
Mm-hmm.
And then you left that and we went back to Hopf Algebras, created Hopf Algebras.
Mm-hmm.
So can we tie these things together?
That's right. So what I want to do next is show you that the similarity is not superficial. That it's not just that the same things are appearing. There's a conceptual reason why the Faa di Bruno Hopf algebra is giving us the same polynomials as as the ones that are coming out of all this stuff. Okay. By the way, I hope this formula looks to you a lot like that one. You have something simple going on with one side and something complicated with the other side, and that's exactly what we have here, where the AK kind of plays the role of the XK over there, and then the BNK plays the role of the B blah 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 over there. And again, there's that slightly annoying shift from n to n plus 1, which comes from labeling the graphs a little bit funny. But what I want to illustrate to you is that this formula is the same as this formula. They're just different ways of talking about the same thing. Okay, so how do I convince you of that? Let's do a little bit more. So, in order to convince you of this, I need to give you a crash course in something called the character group of a Hopf algebra. Okay, and this is something that will play a pretty important role later on. And so later on, I'm going to give you a more detailed account of this. So what is a character of a Hopf algebra? Oh, by the way, before I go into that, let me say that in the notes, I actually derived the formula for C using partial Bell polynomials. And so you should look at it so you see how really combinatorially you write everything down explicitly, and you get a formula like this. So a character of a Hopf algebra H is just an algebra map from H to the field. So in other words, so I need to be linear. I need to be multiplicative. And I need to send 1 to 1. Okay. That's what it means to be an algebra map. And again, we'll see why characters play an important role. Let me make a proposition which maybe you can guess already, because I'm talking about the character group. And so the fact is that this is a group. Okay, so the set of characters this is math BVX. Set of characters in LaTeX, yeah? / math BB of X. The set of characters is a group under what? What operation can you do to characters? So given two characters, how do you operate? Can you compose them? You can't really compose them because they go from H to K. So you can't compose two functions from H to K. Another thing you might try is you could add them. But if you add them, then the result is not going to be multiplicative. Then the next thing you could say is, well, maybe I can multiply them, but if you multiply them, then it's not going to be additive. And so Sam's suggestion is right. What I should do is take the convolution. Which makes sense because we have a Hopf algebra. And so And
that thing, yeah. That thing, the set
the-
of vectors, something G.
oh,
What's that? How do you?
math db.
That's my. It's 2 lines. Sorry.
Yeah. So I'm making a non-trivial and interesting claim here, which is that if you take 2 characters, then the convolution product is also a character. In other words, additivity is pretty hard. It's pretty easy. Multiplicativity, you can check it, and I wrote it in the notes, but maybe I'll delay that for when we talk more about characters. But for now, I just ask for you to trust me that this is a group under convolution. So what is the product? It's the product of f and g is convolution. So remember how that looks. This is the sum in Sweetland notation of f of a of 1, g of a of 2. So this is the product. But to be a group, I need something else, right? Well, I need an identity. So what is a character so natural that it should be the identity? What is this? Do you know any algebra math from H to K? Epsilon is the one we keep talking about all the time, and it turns out to be the right one. So the co-unit is the identity for this, and what is the inverse? What do you think? What do we have in a Hopf algebra that is kind of like an inverse? Huh? The unit is like a unit. The antipode. Let me make again this point because it's very important. An antipode is a kind of an analog to an inverse. Okay, and it precisely does what we want here. So if you want the inverse of f, you just do f of the antipode. And it's kind of cute. You compute it, and it's easy to see that the convolution of f and fs is the identity. This comes from the fact, if you remember, that in the convolution algebra, the identity convoluted with the antipode was equal to this. Okay. Yeah. I star s was equal to u epsilon, and that's what this boils down to. Okay. Okay. So every Hopf algebra has this group of characters associated to it. And so in particular, the Faa di Bruno algebra does too. Okay, and so let's see, where should I write? I'm kind of stuck here. I'm going to leave this here, and maybe I'll just ask you to remember that this looks so much like this. Okay, they look very, very similar. So the proposition that I would like to make is that so this is it's actually from the paper that I was telling Stephen about. Doubilet-Rota-Stanley, they proved the following. The group of characters, the character group, of the Faa di Bruno algebra is almost isomorphic anti-isomorphic.
Actually, back up and ask a question here.
Uh-huh.
That supposed to be x of h is a group under composition?
X of, yeah, thank you.
I only asked that because I want to know what I'm reading.
Yeah, I should have written the set of characters x of h because there's no g anywhere. Is isomorphic, except anti, to the group of divided power series how did I write them here? You try to use the same notation. So I consider all the formal power series, the ones that have no independent coefficient and linear coefficient equal to 1. And these also form a group. What is the operation here? Now it's what you suggested. Right, so now it's composition.
When you say that two structures are isomorphic, it means that they have more or less the same structure. In English, how would you say what it means to be two things for them to be anti-isomorphic?
So anti-isomorphic means that they're the same structure except backwards. So in one, the product is g times h, and in the other one, the product is h times g. So they're exactly the same structure except that you're multiplying left-handed somehow. That's what anti-isomorphic means. It's like isomorphic when you look at it in a mirror, I guess. There you go. That's anti-isomorphic.
When you write it down, you take that into account, right? So it still is actually isomorphic as well. It's just you're sort of specifying a kind of particular kind of isomorphism.
Yeah. I guess it's just very naturally isomorphic to this guy, and then, there is the mirror isomorphism that can twist it for you. That's right. So what's the point? The point is that computing in the Faa di Bruno Hopf algebra is going to be equivalent to, computing in the characters of this guy is going to be equivalent to composing power series. Okay? And so it's not an accident that we're getting the same kinds of expressions here, because all these, the formulas that I just erased, are precisely about composing power series. Or for example, this one right here is precisely a formula for the inverse in this group. Right? This is the group under composition. And so taking F inverse is precisely, this is precisely the formula for the inverse in this group. Okay. And maybe I won't try to rush this, but let me just say, I'll write it down. So a corollary of these two statements is that the antipode of F is given by the exact same formula. Because the point that I want to make is that finding the inverse here is the same as finding the inverse here, and inverse now is the antipode. Okay? And so it's not an accident that these two formulas are the same, because this more conceptual theorem explains that they should really look the same. Question?
Yeah, so it seems weird that there's a zero cost in there. And I feel like the effect of that is that it sort of makes certain terms in the polynomial go away.
Mm-hmm.
Is there some sort of natural interpretation for which terms those are?
Yeah. So let me just make a closing comment that I'm gonna be more detailed about everything that I said today in the next class. Okay. I wanted to kind of close the story and show you where we're headed, and then we'll be a little bit more careful about proving all these different things next time. Okay. But that's kind of the big picture. To go back to Seth's question, that's exactly right. That plugging in 0 precisely has the effect of killing a bunch of terms in these partial Bell polynomials. What terms does it kill? They're precisely the terms. I mean, remember that all these terms come from taking the number n, the set n, and splitting it into groups. If you have groups of size 1, this 0 kills them. And so the effect of this 0 is precisely killing everything that has terms of size 1 and letting survive anything that has terms of size 2 or bigger.
So we're getting rid of isolated vertices.
And so effectively what we're doing is exactly getting rid of isolated vertices, because the isomorphism wants to kill those. That's right. Yeah. I don't know why this is still recording it, but anyway, that's a good place to stop, and we'll be a little bit more detailed about this next time.